Inside a fully booked restaurant during the Friday evening rush, every square foot of space and every minute of time is actively accounted for. Digitizing this floor plan creates a structural conflict. The platform must provide massive distributed scale for discovery while maintaining strict sequential consistency for inventory. On the read side, millions of monthly users execute complex 30-mile radius spatial queries simultaneously, expecting instant availability across thousands of locations. On the right side, the system faces hotspot contention. This happens when hundreds of those users compete for the exact same 7 p.m. Friday table at a single popular venue. If the system processes these requests concurrently without a coordination layer, it risks double booking the physical inventory, leaving two distinct parties to arrive for the same table. The engineering goal is to maintain sub-200 millisecond spatial search latencies while preventing any concurrent double bookings. Legacy monolithic ACI databases struggle with this dual mandate. The locking overhead required for millions of searches can choke the transaction engine, making a decoupled microservice topology necessary for survival at scale. Because reservations involve financial transactions and physical inventory limits, the baseline system of record must be a relational database like PostgreSQL to prioritize data integrity. This schema connects branches to tables, linking to customers through a centralized reservations table. To prevent overbooking, operational constraints require the seating capacity column to be at least 1. For large parties, a table allocation junction table binds multiple table IDs to a single reservation. While this setup secures the data, a static schema cannot rapidly compute the fluid combinations of tables needed to maximize a restaurant's hourly yield. PostgreSQL secures the state, but running combinatorial logic queries directly against it will throttle the system. Calculating true availability requires moving that logic into a programmatic layer. Finding an available table is formally modeled as a constraint satisfaction problem, or CSP. This 2D Gantt chart visualizes the CSP. Each reservation request contains a start time, end time, and guest count. The end time computes dynamically using historical meal durations. Finally, a temporal disjunction constraint ensures overlapping reservation intervals cannot be assigned to the same table. To solve these constraints in real time under heavy transactional loads, the system implements a variable ordering heuristic. This heuristic prioritizes requests with the tightest table compatibility. Seating the most constrained parties first prevents the dining room floor from fragmenting into unusable gaps. Treating availability as a dynamic CSP maximizes seating yield, but computing this for concurrent users requires decoupling the search engine from the transaction engine. Postgres faces significant latency spikes and connection queuing if forced to process millions of spatial searches while simultaneously solving constraint algorithms. We resolve this by offloading the read path. Search traffic bypasses Postgres, routing directly to an Elasticsearch cluster for 30-mile radius proximity searches, kept accurate via a continuous synchronization stream. However, on the write path, if two users see the same table and click Reserve simultaneously, they trigger a race condition. To intercept this race condition, we use distributed locking via a Redis coordination layer. Redis manages contention using the setNX command. The first request claims the table key, while the second is rejected. The command includes a PX 300,000 parameter. This creates a 5-minute slot lock, protecting the inventory while the user completes their transaction. One diner proceeds to checkout, while the other receives an inventory unavailable error. While Redis prevents race conditions, holding a lock for 5 minutes causes a deadlock if the user's payment processing fails or times out. The checkout process is a distributed transaction across microservices. Every step, from locking inventory to processing payments, must either complete successfully or be rolled back entirely. An orchestration-based Saga pattern coordinates this flow. The central orchestrator first contacts the inventory service, changing the table state to hold. Next, it hits the payment gateway with an item potency key. Finally, it updates the PostgreSQL database, locking the reservation as booked. If the payment gateway fails, the orchestrator fires a compensating action to release the Redis slot lock, returning the table to the available search pool. This Saga pattern ensures eventual consistency across the distributed environment, preventing a failed transaction from permanently locking physical restaurant inventory. Zooming out, we see the finalized architecture processing a completed booking. Once committed to Postgres, The system publishes a booking confirmed event to an Apache Kafka queue. This stream fans out real-time availability updates to the restaurant's tablets via WebSockets, instantly refreshing their floor plan. The Diner portal handles these updates using isomorphic micro frontends, executing Node.js closures server-side to ensure near-instant rendering for the user. The architecture is built to manage the tension between high-velocity geographical discovery and the strict transactional requirements of scarce inventory. Elasticsearch provides the scale for search. Redis manages concurrency. Saga ensures transaction safety. Postgres maintains the record of truth. Managing high concurrency booking at a global scale requires chaining specialized coordination tools to synchronize state across time and space.